Okay, welcome back. We'll get started very soon. So it's very nice to see as many people coming back for the third lecture. I should say that in my 20 years of Simon's lectures and pure and applied, the turnout at the third lecture has not always been that great. So that's a testimony to Thomas Vidick's lecture. So today is going to talk on quantum PCP conjecture, quantum codes, and high-dimensional expanders.
Thanks, Michel, and so thanks for coming back. So you're very brave, so I hope I make it worth your time. So this lecture is self-contained compared to the other ones. So I'm going to talk about, but the connection I kind of like sketched in one of my last slides on Monday, if you were here Monday. So our starting point was a constraint satisfaction problems that are studied classically in complexity theory. And we obtained a quantum generalization of constraint satisfaction problems by thinking about them in a particular way. We thought that the constraint satisfaction problem is a set of constraints on variables. And I presented it as, these variables are obtained as results of observations on the universe. And how do we model making observations in the quantum setting? We had a Hilbert space, and the outcome of each observation, so the value of the variable, is obtained through an observable, which is an arbitrarily dimensioned matrix on the Hilbert space, okay, whose spectrum encoded the outcomes. And that's one analogy we can make, and today I'm making a different one. So that analogy there was like thinking about the process that generates the variables as quantum. Now we're going to think in the kind of like a Schrödinger picture, just putting the variables first and generalizing bits to qubits. And one important difference compared to before is that the dimension of a qubit is 2. So there will not be arbitrary large dimensions. There will not be infinities. There will not be undecidable problems in the lecture. We're going to stay like more closer to Earth. So I don't know of any connection between what I talked about in the previous 2 lectures and this one, other than this like philosophy that I just tried to communicate to you. But there might be. It's just they haven't really been unearthed yet. Okay, so there's 2 parts. So the first part I want to introduce you to a large portion of quantum complexity theory, which is called a quantum Hamiltonian complexity. So they're complexity theoretic problems that are motivated by many body systems in physics. So this will just be an introduction by way of example, okay? And my goal at the end of that is to state informally this conjecture, which is an important conjecture in quantum complexity, the quantum PCP conjecture. And then I'll make a jump. I'm just using the conjecture as motivation to study quantum codes. Okay, quantum codes are sort of like an approach or a step towards studying this conjecture, and I will define quantum locally testable codes by starting from classical codes, generalizing to quantum, and just point out a very nice connection between trying to construct such codes and an area in let's say combinatorics called high-dimensional expansion. Okay, and that will be it. All right, so for part A, I'll start with examples. In fact, I will only do 1 or 2 examples. So let's imagine that we fix a graph. And I think of V as my collection of variables. So let's say that V is just the integers 1 up to n. And to this set, I can associate a Hilbert space H, which is just, I place a copy of C2, let's write it like this, at each of the vertices. Okay, so I have this Hilbert space whose dimension is 2 to the number of vertices. And I will construct what's called a Hamiltonian on that space, so a set of constraints on this Hilbert space. So I'll start with a classical example. So consider this matrix. Okay, it's a 2 by 2 matrix. It's diagonal. The eigenvectors are, so this is just to set some notation. So E0, E1, 0, 1, and so I can rewrite this matrix as just the projection on E0 minus the projection on E1. But the way I think about this matrix is as an energy potential. Okay, so it's also a linear operator acting on C2, and it assigns energy +1 to this vector and energy -1 to this vector E1. And more generally, it assigns an energy to each vector, any vector u in C2, simply through the formula UZ U like this. Okay, so this is going to be a real number between -1 and 1, and I think of it as the energy of some state or configuration U with respect to this energy potential. Now this is just for like 1 qubit. It's a 2 by 2 matrix. I can apply it on my space here. So this is another piece of notation for I between 1 and n. I will define Zi to be the identity. So this is 2 by 2 identities everywhere except in the ith location. I put a Z matrix. Okay, so now this is a 2 to the V ith location, 2 to the V by 2 to the V matrix, but it's trivial, everywhere except in this ith position here. Now, when I write something like Zi tensor Zj, okay, so I think of this. I'm a little bit sloppy in my notation. It's by this I really mean maybe I should write Zi times Zj. Okay, I will use these two notations interchangeably, and this is just also identities everywhere, and I have Z in the, okay, I think hopefully you see what I mean. So I have Z in the ith location and Z in the jth location. Okay, I different from J. So now I think of this as a parity constraint on my system. So if you, how to see that? So if I take, I can take a vector U and compute U transpose Zi tensored Zj U. Okay, this matrix has eigenvalues +1 and -1. Okay, as a matrix in the appropriate basis, it's just 1 minus 1 minus 1, 1. And so this is going to be equal to +1 times the overlap of U in the eigenspace with associated eigenvalue +1 and this square, where what is this? This is the projection on the span of all vectors such that in the locations I and j, they're of the form E0 tensored E0 and E1 tensored E1. Okay, these are this basis state and this basis state. They're the ones that are assigned energy +1, and this is the projection on the span of E0 tensored E1 and E1 tensored E0. Okay, so again, I think of this matrix as an energy potential now on the entire space, and it's assigning energies +1 to vectors such that when I expand them in the standard basis of the entire space, the coordinates I and j lie in the span of these two vectors, and -1 if they lie in the span of these two vectors. Okay, if they lie in the span of, don't lie in one particular span, then I will have an energy that's between -1 and 1, depending on like how much L2 mass is in one span or the other. All right. So now, I had a graph. I only used the vertex set so far, not the edge set. So now to my graph, I'm going to associate the following Hamiltonian. So we call Hamiltonian in general any Hermitian matrix thought of as an energy potential. So we'll just take H equals 1 over E sum over all edges. So the edges are undirected of Zi tensored Zj. Okay? So this is something that gives me energy -1, which we think of as favorable. We're generally interested in minimizing the energy. For whenever I have an edge, my vector or my state is in the span of basis vectors that have odd parity with respect to that edge. As a matrix, it's a matrix that's diagonal in the standard basis, okay, because the Z matrices are diagonal in the standard basis. I can take a basis vector Ex. So Ex is just some notation for Ex1 tensored Exn. So X is just a string in 0, 1, n. And I can compute the overlap of that particular vector on H. And it's going to be, by linearity, sum over Ij in E. And here I will have 1 if Xi is equal to Xj, and -1 if Xi is different from Xj. Okay? So I will say that this basis state has energy, this number with respect to the Hamiltonian. So if we're interested in minimizing the energy, I will minimize, because the matrix is diagonal, it's enough to minimize over basis states, so I will minimize, let me write it here, minimize over x of Ex transpose Hex. This is going to be 1 by E. And here, this expression, I can just rewrite it as as the number of edges minus total number of edges minus twice the number of cut edges, where an edge is cut if the xi is different from edge j. So this is just equal to the number of edges minus twice the largest possible cut in the graph G. Okay? And because my Hamiltonian H was diagonal in the standard basis, this is equal to the smallest eigenvalue of H. Is this okay, the notation? So what I demonstrated here is that you can encode certain classical constraint satisfaction problems, such as the max cut problem, in Hamiltonians. Okay, so I had a graph. I designed a very simple Hamiltonian associated to it, such that the smallest eigenvalue of the Hamiltonian captures the largest size of the graph. In particular, because the max cut problem is NP hard to solve, even to approximate, I get the following corollary, which is that for every epsilon, there exists epsilon positive, such that approximating, so such that given H approximating the smallest eigenvalue of H to, let's say, additive plus or minus epsilon is NP hard. Okay, here I haven't been very clear what I mean by given H. I haven't specified like the class of inputs that I allow. I allow all local Hamiltonians. I don't want to define that precisely, but think of it as Hamiltonians that have a relatively simple form, so they can be expressed as linear combinations of local terms, where this was local because it was identity on most of the copies of C2 and something different from identity on the other copies. I'm going to give you another example of a local Hamiltonian. Hopefully it will make clear what class of Hermitian matrices I'm talking about. What's relevant is that even though this matrix is exponentially large, okay, it's 2 to the n by 2 to the n, I have a succinct description of it. To describe it, I only had to specify the graph, which has size just n squared or something like this, the number of edges. All right, so this is all very classical. Now I want to say something a little bit quantum. So in quantum mechanics, we know that we have other matrices than the matrix Z, so other bases than the standard basis. So I can consider another matrix now, which is this matrix. Okay. So the eigen decomposition of this is we'll call them E plus. So it has plus minus 1 eigenvalues. You can check that it squares to identity, and it's equal to this, where E plus is just the vector 1 over root 2, 1, 1, and E minus is 1 over root 2, 1 minus 1. Okay. So now, given this, I can construct the following. Maybe let me just take the other board. Okay, sorry, I'll do it here. Let's consider the following Hamiltonian for now on 2 vertices or 2 qubits to keep it simple. So I will put a factor minus. This is just for normalization, and I will consider x tensor x plus z tensor z. Okay, so x and z, you can verify that they anti-commute. Okay, when you commute, you pick up a minus sign. Now x tensor x and z tensor z, when you multiply them, each factor will anti-commute, so you will pick up a minus and a minus, which gives you a plus. So these two operators commute, which means that they're simultaneously diagonalizable. So the eigenvalues of this operator will again be plus 1 and minus 1. And I can compute what they are, and I'm not going to do it on the board. I will just say one relevant thing, which this has eigenvalue minus 1, and it has a unique associated eigenvector. So 1 has multiplicity 3, minus 1 has multiplicity 1. And the associated eigenvector is called the EPR pair in quantum information. So it's vector u, which is equal to 1 over square root 2 E0 tensor E0 plus E1 tensor E1. Okay, so as a 4-dimensional vector, it's like this. Okay. In quantum computing, we would call this vector entangled because it's not a tensor product. Okay, you cannot write, you can try to do this as an exercise, but this vector cannot be written as a tensor product of like A tensor B. All right. Okay, so now I can construct, I can do a new Hamiltonian, but instead of Zi tensor Zj, which is some kind of classical parity, I will put this constraint instead. So I will define H prime, which is equal to 1 edge sum over Ij in E of minus half Xi tensored Xj plus Zi tensor Zj. And now you can start studying the problem of what is the smallest eigenvalue of this Hamiltonian and how hard is it to compute. And it's a very interesting problem. In particular, it's interesting even for bipartite graphs. So I could consider a graph that's like this. Okay, maybe there's more vertices, but let's just say that it's bipartite. So for bipartite graphs, the max cut problem is very easy to solve. You can cut all the edges by putting the x's on the left equals to 0 and the x's on the right equal to 1, and so it's very easy to solve. Here, if I try to minimize the energy of this Hamiltonian, what am I trying to do? I'm trying to find a vector, so it would be some vector u in C2, tensored v times, such that whenever I consider the restriction or projection of this vector u on an edge, so the kind of four-dimensional restriction, I'm saying this a little bit loose, it should ideally be proportional to the only eigenvector with eigenvalue -1 of this Hamiltonian, which is the vector that I wrote here. So in order to satisfy all the constraints, I would like my vector, when it's restricted to this edge, to look like E0 tensor E0 plus E1 tensored E1. Okay? But when I restrict it to this edge, I would like it to look the same, E0 tensored E0 plus E1 tensored E1 up to normalization. And again, it's an exercise that there doesn't exist a 8-dimensional vector such that when you consider the restriction to the first two factors, you would get something proportional to this, and the other two factors, you would get something proportional to that. In other words, this Hamiltonian is frustrated. It's as long as the graph is not just simply a perfect matching, you cannot satisfy all the individual terms exactly. So this quantum information is called monogamy of entanglement, but it's just it's an exercise in linear algebra to see that you cannot do that. Okay. So now we start seeing something a little bit interesting, which is that well, it's not obvious what the smallest eigenvalue of this Hamiltonian is, and it's also not obvious how I'm going to represent eigenstates of it. Okay, the previous one was diagonal in the standard basis. Eigenstates were just tensor products of elementary basis states. Here, my eigenstates will be, sums of tensor products. It's not clear at all how to put my hands on it. So let me maybe go here. So the conjecture, the quantum PCP conjecture, is that maybe I should. Where did I write the statement about? I erased it. Maybe I just erased it now. Okay, never mind. So the conjecture, the quantum PCP conjecture, is there exists epsilon positives such that approximating. So given a Hamiltonian, a local Hamiltonian, this is another example of a local Hamiltonian, approximating the smallest eigenvalue of the Hamiltonian to plus or minus epsilon is, we already said that it's NP hard. So the quantum PCP conjecture states that it's harder. Is the quantum version of NP hard, QMA hard? I don't have time to define QMA for you, so just think of it as being harder. In particular, in particular, this. But an implication of this conjecture is that NP is the class of problems that can be verified given a classical witness or proof. Max cut, you can verify that the max cut of the graph is above a certain value simply by given a cut that satisfies this value. The conjecture implies that for these kinds of Hamiltonians, there should not exist some kind of a succinct description of a vector in the space such that by checking the energy of that vector, I would certify that the smallest energy is something. So in particular, it implies that eigenstates associated to all the small eigenvalues of H prime, so all the ones that are within this regime, should not be product states, and they should not be something close to product states, and in fact, they should not have like a simple description from which I would be able to compute, verify the energy.
So in this conjecture, is that H, should that be H prime?
Well, no, it's H. I mean, such that given as input H, given H as input. So I see. So I haven't specified so I can specialize it. I could specialize it to, given a graph as input, okay, define H prime as follows, which only depends on the graph, and the smallest eigenvalue of H prime is hard to approximate. This would be a stronger conjecture than the one I want to make. I want to make the conjecture that this value is hard to approximate, not only for these H primes, but in fact, any class of Hamiltonians that has an expansion as a linear combination of terms of the form xi tensor xj, but maybe also tensor zk or things like this. So like I want to consider a slightly larger class of models.
Okay.
This was just an example. By the way, this example is motivated by physics, so it's known as the antiferromagnetic. It's like a slightly special case of the antiferromagnetic Heisenberg model in physics. So
you said that deciding if this lambda min of H is 1 or -1 is easy, is it?
For this, no. For this particular case, yes, it will be -1 only when the graph is a matching. But this is just a special case. Like in general, no. So there are other questions. Like now I want to seg into the second part, which I will not revisit this problem. I'm using it only as motivation to say, okay, like now our goal, if we want to prove that, is to try to construct classes of Hamiltonians. You know, not necessarily this one. I will construct some other ones later on. But that are similarly simple, but such that I can prove that all the eigenstates with eigenvalue equal to the minimum or close to the minimum must be complex. And we will do this by constructing error correcting codes. So it will turn out that quantum error correcting codes give us Hamiltonians, and I will say how. Such that if the error correcting code has an additional property of being locally testable, which I will define, then this gives us a way to put a handle on not only the eigenstates with smallest eigenvalue, but with a bit above. Maybe I should clarify that the content here is really in the epsilon, so we know that this conjecture is a theorem for the case where I replaced it by computing the smallest eigenvalue, so it's a theorem, and also approximating it to precision that's inverse polynomial in the system size. So the contents is really that, even though these are non-trivial theorems, but they're known, the contents of the conjecture is that the problem should remain hard to some constant approximation accuracy. Okay, so it's the step from showing that max cut is NP hard exactly to max cut is NP hard to approximate, which is the PCP theorem for people who know.
It's really just saying that these two problems are equivalent. That's a proxy for
That would be the same. Yeah, that would be the same. Right. So yeah, thanks. So I'm going to talk about codes, and I'm not assuming too much background in codes from the audience, so I will actually be spending quite a bit of my time on classical codes, but I will try to present it in a way that the extension to quantum codes appears natural. So, okay, so this is part B. So definition. So I look only at linear binary codes just for simplicity. So there's 3 parameters that are important when you study codes. So an NKD binary linear error correcting code, classical error correcting code, is specified by a subspace, I will call it C, of F2 to the N, such that, so this is the N parameter, okay, such that the dimension of the subspace is equal to K, and the D parameter is the distance of the code. I will let me write this in a second. Okay, I will write the definition of the distance in a second. So a general way to specify a subspace is as a kernel of a linear matrix. So in general, codes can be represented as kernel of a matrix H, H is called the parity check matrix, so it's in F2M. M is the number of parity checks times n, and if the kernel of H has dimension k, then this kernel is an error correcting code that has parameters n, k, and some d that I will specify in a second. So I can think of this parity check matrix as a linear map, right? So equivalently, a matrix is a map, and I will call this map delta, from F2 to the n, so the space of my bits, to F2 to the m, which is the space of my parity checks. So I want to draw an example. So one way to draw my code is through what's known as the Tanner graph. So I can represent here the bits of the code. So this is F2. I mean, this is a way of representing the space F2 to the n, where n is equal to 3. I will call this space C0. And I can represent the parity checks here. So like this, let's say there's 2 parity checks. I will call the space of the parity checks F2. Okay, so it's F2 to the m, it's C1, and the parity checks, I represent them like this. Okay, so this is the repetition code. This is a way of representing this matrix here, H to be 1, 0, and 0, 1, 1. Okay, so the first parity check is parity of the first 2 bits, and it's this, computes the parity of these 2 bits, and this computes the parity of these 2 bits. Okay, so that's just a picture, and I think of my parity check matrix as a map that goes to here. Okay, so given any element of F2 to the n, I can compute, I can evaluate the parity check matrix on it. Now let me give you the definition of the distance. I will just record it here because later I will extend the definition to the case of quantum codes. So the distance is simply the smallest Hamming weight of a non-zero word in the code. So it's the minimum of Hamming weights. Okay, this is the Hamming weight, the number of non-zero entries, such that x is in the code. So saying that x is in the code, it's the same as saying that it's the kernel of the parity check map, non-zero. So in error correction, we try to design codes that have these parameters as big as possible. So ideally, the dimension would be linear in n, because this says like how much information we're able to encode in our n bits. And the distance would also be linear in n, because this says like how many errors we can correct. All right. So now locally testable codes. So I will add one condition here. So we say that the code C is Ho. So Ho is going to be a parameter between 0 and 1, and it's Ho locally testable if for every x, the weight of hx is bigger than Ho times the distance of x to the code. Okay, so I want to explain this condition. So when you take an arbitrary error correcting code, and now suppose that you're given a word, so an element of F2 to the n, and you want to know if this word is a code word or not. What do? You evaluate the parity check matrix just to check that all the parity checks are satisfied. If all the parity checks are satisfied, you know that it's a code word. What if not all the parity checks are satisfied? In general, the definition of the code says nothing. If one parity check is not satisfied, it's not a code word. Okay, so it has weight larger than the distance, and that's it. Locally testable codes give us a stronger condition, which is that when we take a word, so this should be, maybe I should specify my spaces. So when we take a word and we evaluate the parity check matrix, the number of parity checks that are not satisfied, okay, so the weight of this is an upper bound up to some parameter Ho that we hope is the largest possible. So this will be stronger when Ho is large, is an upper bound on the distance to the code. So think of it as if I satisfy most parity checks, this is small, then up to 1 over Ho, this is going to be small also. I'm going to be close to the code. Okay. So, like if you're like a little bit ahead of me, you can kind of see how this is maybe going to be related to the problem that we were worried about before, because this gives us a little bit of a control. It says that words that have low energy, okay, that satisfy most of the checks, are close to the code. And this is like something that gives me a handle on what low energy words look like. But this is all classical. So now, for motivation, I want to try to talk a little bit about how would you prove that the code is locally testable. So it turns out to be something that's pretty hard. In particular, I guess Alex Lubotsky was here like some weeks ago, maybe talking about the first constructions of locally testable codes that have a constant parameter whole and k and d, which are both linear in n. So this was only discovered like some years ago. So if we think about how would you prove this, so let me make a statement. So the locally testable property requires redundancies in the parity checks. Redundancies in the parity checks. So what do I mean by this? So imagine that my parity checks were all linearly independent. Okay, they specify a subspace and they're linearly independent. So now if I erase one parity check, because they were linearly independent, I will get a subspace whose dimension has increased by 1. So I will suddenly have a whole lot of words x that satisfy all the parity checks but 1, okay? And these words, now you can take the sum of code words plus this extra dimension. These are in general things that will have large weight. This extra dimension that you added will in general have large weight, so there will be words whose distance to the code could be large, but they fail only one parity check, okay? So having linearly independent parity checks is not a way to achieve local testability. You're going to need linear dependencies. So let's express these linear dependencies through another map. I will call it, so I need to add a 0 here. And I will consider the situation where there's linear dependencies between the parity checks, and I will capture those using another linear map. So let delta 1 be a map that goes from the space of parity checks, f2 to the m, to some other space. Okay, it doesn't matter to me what is here, so I don't know, f2 to the o, such that the composition of the two maps, so delta 1, delta 0, is equal to 0, okay? So any such linear map expresses linear combinations between the parity checks, okay? You can think of this as if these are matrices, so each row of this matrix, delta 1, is a linear combination of the rows of delta 0, which is equal to 0. So on my example, sadly, I don't have linear dependencies between these checks, but if I add a third one, I'll just do it in blue so that it stays readable. So we'll add a parity check here. Okay. Now my parity checks are linearly dependent in the sense that the sum of the three parity checks is always equal to 0. Okay. What I mean by this is just that there is not, whenever you put a word here and you compute which parity checks are satisfied and not, the sum of the three flags that you get here will always be 0. And I can represent this in this way. Okay, and so this is my map delta 1, and it goes to some space C2, which I called F2 to the O. Okay, so now I want to discuss like a strategy for showing that the code is locally testable. How would you show that such a condition is satisfied? The strategy, so this is not the only possibility now, but a natural strategy to adopt is that, okay, so you take a word, so you're considering an x which is situated here, okay, so your x is some element of this space, and when you compute this map delta 0 forward, then you know that the number of parity checks that is not satisfied is small. Okay, if it's large, then the inequality is true. So let's assume that it's small. So maybe there's just a couple parity checks that are lit up. And your goal is to show that this x is close to the code space. And you can try to show this by a local strategy. By this I mean, okay, so let's try to reduce the number of parity checks that are lit up by making small modifications to my x. Let's say my x was 1 here. I will change it. I will change it to 0. And hoping that by having made a local modification to x, I will manage to remove this parity check from being lit up, and only this parity check will be lit up, okay? And if whenever there are some parity checks that are not satisfied, I can always reduce the number of parity checks that's not satisfied by making a local change to my word X. I will have proved a local testability, okay? Because by iterating this process, I will eventually arrive in a situation where all the parity checks are satisfied, so it's a code word. And how many changes did I make from my X to arrive at the code word? A number of changes that's proportional to the number of parity checks that I had to erase. Okay, so in this way, I've managed to show local testability. In other words, local testability is going to follow from another parameter. So the goal of this discussion was just to justify the introduction of a slightly stronger notion of distance. I will define here, let me copy, sorry, I will copy the rho here in case it gets erased later. So rho is the minimum of, I can define this local testability parameter as the minimum of the ratio of the image of an X divided by the distance of X to the code for all X's that are not in the code, otherwise I'm dividing by 0. So X in C0 minus caret delta. And my last parameter is called locally minimal distance. So I will write it as loc. I will put a 1 because it's a distance parameter that I think of as here, right? It's interesting, but I have a matrix here, and this matrix has a kernel, and I could think of that as a code and ask, okay, does that code has a distance? So it doesn't have a distance. Why? Because any element that's in the image of this map must be in the kernel of the other, right? That was my requirement. But there are elements that are in the image of this map that have high weight. If you take like a random word here, in general, a lot of the parity checks will be lit up, and this will be an element in the kernel of this map that has high weight. Okay, so just considering the distance of the kernel of this map is not, this is not a good idea. Instead, we consider the locally, called locally minimal distance. So this is the smallest weight of an element X that's in the kernel of the map, okay? But under an additional condition, the additional condition is that it's locally minimal. What does that mean? It means that for every Y in C0, such that the weight of Y is equal to 1, so any small thing in C0 will not reduce the weight of X. So X plus the image of Y should be bigger than the weight of X. Okay? So I can define this, the smallest weight of a word that's in the kernel of the other map, and that cannot be reduced. So these, in a way, think of these as obstructions to local testability, right? Any such thing prevents my strategy, the strategy I described to show local testability, to work. Because if I have something that has a certain weight here, and let's say this is small, it's a combination of parity checks that I cannot reduce, whose weight I cannot reduce by making small modifications to the element that I started from. Okay? In particular, you can show, I will not show it to you, but it's because of time, but it's a very simple local argument. So it's this is a true claim. So claim the local testability parameter is bounded by this locally minimal distance. So it's at least this. I need to normalize properly, so these things are kind of like extensive, so it scales with the size of the space. And this is intensive. It's a number between 0 and 1, so I need to normalize, and the proper normalization is this. So it's just in my case, this was just that. Okay. So if you manage to show that this distance is linear, then you've managed to show that the code is locally testable. So I adopted how do you say, notation that's suggestive of the area of chain complexes. So maybe some people here study chain complexes. So a chain complex is exactly this. It's just a sequence of vector spaces with linear maps between these vector spaces that satisfy this condition here, that when you compose the map twice in sequence, you get 0. And the parameters that I introduced, the distance and this locally minimal distance, and also the local testability parameter, this is called the co-cycle expansion in the language of complexes. So it's natural to think, I didn't say this, but as an expansion parameter, right? Because it's asking about strings here. When you apply the co-boundary map, so strings that are far from the code, when you apply the this is called co-boundary map. So the parity check matrix, they should their weight should expand, or like let's say not shrink too much. So the purpose of all this was to give you like definitions about classical definitions about codes, and relate these definitions to this picture to kind of justify that the task of designing good locally testable error-correcting code is the task of designing is equivalent or reduces to the task of designing chain complexes. So these like two-step maps like this that satisfy the chain condition and have certain expansion properties. So I will not show you how these things are constructed. This is like presumably what Alex talked about in his talk. But let me just say just a word about how you would go about constructing such things, because, and then I will move to the quantum case. It turns out that these are obtained from geometry or topology. So why? So this is not necessarily, okay, but a big source of constructions, they look like this. So you take a surface, it could be a donut, but I'm just like drawing a ball here, and triangulate it. So something like this. Okay, and imagine triangulating the whole surface. So I can associate a chain complex to this in the following way. So I have three natural vector spaces. I can consider a vector space that's associated with the vertices. Okay, so this is V is just a set of vertices in my triangulation. I can consider a vector space that's associated with the edges. Okay, so this is just something that has dimension, whatever number of edges I have. And also I can consider something that's associated with the faces. So in this case, the faces are triangles, but I could consider triangulation by squares if I wanted. This would be fine. And there's a natural map that goes from vertices to edges and from edges to faces. And this is called the co-boundary map. So it's the inverse of the boundary map. So what is that map? So take a vertex. Okay. So this vertex in my example is adjacent. Okay, I need a proper triangulation. So is adjacent to 1, 2, 3, 4 edges. So the map will send the indicator vector of that vertex, okay, the vector here that has a 1 only in that location, to the indicator vector here of the 4 edges that touch this vertex, okay? So if it's this vertex, it will be sent to these 4, this vertex to these 4, etc. Similarly for the edges, so if I consider I want to define a map here, I will just say that it will send the indicator vector of an edge to the indicator of all the faces that touch that edge. So in this case, there was only 2 faces, these 2 faces. And now it's a basic fact of yeah, you finish it up linearly. You're right. So these are linear maps. Yeah. And it's a basic fact of I don't know what to call it, like geometry or topology, that the composition of these 2 maps evaluates to 0. So I can do a proof by example. So let's start from this vertex, and we apply the map to it. So this is just indicator of that vertex. I get these 4 edges, right? And now I apply the second map from edges to faces. I will get, so this edge will send me just that face. There's nothing here on the outside. So it will just send me that face. This edge will send me these 2 faces. This edge will send me these 2 faces. And this edge will send me that face. Okay, and you see that each face was obtained exactly twice. Because things are done over F2, there will be cancellation, and I will get 0. So for any vertex or set of vertices that I start with, if I apply my maps twice, I will get 0. Okay, and this just works for any closed surface that I can consider. And so in this way, you're able to construct chain complexes and hence potentially locally testable codes starting from surfaces and triangulating them. And then you can ask the question, okay, if I want a good parameter for local testability, what does the surface look like? And so you start studying like things like isoparametric inequalities on your surfaces. Like I don't want to go into that. I just wanted to like show the connection because this is how the locally testable codes are constructed. No, so you can do this in any dimension, but then you will have you will consider so it doesn't need to be vertices, edges, and faces. You can consider higher dimensional. And in fact, this will show up in the quantum case that I'll discuss now. No, it doesn't need to be. It can be a surface in any dimension. So, other question? Okay, now I want to move to talk a little bit about quantum codes. So, and the punchline is just going to be that quantum codes is the same, but we need to go 2 dimensions higher. So instead of having a change complex of length 2 here, I will have something of length 4 with 5 spaces. And constructing these things will be what is needed to construct quantum locally testable codes. Okay, so why? So we will need to consider not only faces, but like some higher dimensional stuff. Okay, so why is that? So I will try to amend my definitions to talk about the quantum case. So what's a quantum code? So it also has parameters n, k, and d. So they will have a slightly different interpretation. So quantum code. Okay, because it's quantum, it's not going to be a subspace of bit strings. It's going to be a subspace of qubit strings, which we already encountered in the first part. So this is just C2 copied n times. Okay, but it is going to be a linear subspace. The dimension of the linear subspace is not going to be k. It should be the dimension that's appropriate to encode k qubits. That would be dimension 2 to the k. Okay, so I want a subspace of dimension 2 to the k. So that's what a quantum code. The dimension I will define a little bit later. Now, just like classical codes are naturally specified through parity check matrix, you can define not every quantum code, but virtually every quantum code that's studied using 2 different parity check matrices. And this is because quantum information, we already saw this before, can be read in different ways. There's the standard basis, and then it's Fourier transform, the Hadamard basis. So we will need to have parity checks in the 2 different bases in order to correct any kind of error that could happen to the quantum code. So I'm not going to develop in 10 minutes the theory of error correction, so you kind of have to like trust me a little bit here that I'm saying the right thing. So a special class of quantum codes called CSS codes are specified in the following way. So I have a particularly elegant and succinct way of specifying such a subspace. How do I do it? So I'm given 2 parity check matrices. I will call them HX and HZ. So HZ is the first parity check matrix, and this will be like a regular parity check matrix. Okay, so there's no complex numbers here. It's over a matrix over F2, and it has mx rows and as many columns as qubits. And the matrix HX in F2 MZ M. Okay. Given any such 2 matrices, I can associate a subspace of C2 to the n in the following way. So it requires a couple steps. I don't want to have too much notation, so I will show you the steps in an example. So suppose that the matrix HZ is the parity check matrix that we already met earlier. So it's this parity check matrix. To it, I can associate what are called stabilizers, but these are just observables, matrices, as follows. So I will define a set SZ, and this set contains 2 matrices. It contains the matrix Z, tensored identity, and identity tensored Z, tensored Z. Okay, so here I'm just telling you how to associate matrices to matrices. So, but this is a parity check matrix, and this is a couple matrices. Similarly, if the HX matrix, so I don't have so much space, so let's just take it to be like this. Okay, so it has a single row. This is a single parity check, and I would associate to it in the same way operators, and now it's natural that I will get XX X. Okay. So now, how is the code defined? It's defined as the simultaneous +1 eigenspace of all these matrices. Okay. So each of these matrices has trace 0. That's easy to verify because Z and X have. So each of them has a +1 eigenspace whose dimension is half the total dimension, and a -1 who's half the total dimension. You can verify that if they are actually, sorry, let me give you the definition first. So I will define C, because this is where we're going to see a Hamiltonian. C, my quantum code, is equal to the -1 eigenspace of the following Hamiltonian, H, equal to minus, I have a lot of minuses, but minus the sum over P in Sx of P minus the sum for Q in Sz of Q. All right? So this matrix will have a non-trivial -1 eigenspace only if all the operators I wrote there commute. Okay? if there's an anti-commutation between the two of them, any two of them, the sum will not have a -1 eigenvalues. The eigenvalues will be bounded away from -1. So to get a proper quantum code, I need an additional condition, which is that all the SZ matrices commute with all the SX matrices. So this is an important condition. The fact that they commute is exactly the condition that the X's and Z's overlap in an even number of positions all the time. So it's exactly the condition that all the rows of HX and all the rows of HZ have even inner product. So I can write that very succinctly as the condition that HZ transpose, no, actually I want HX, let me write it this way, sorry. HX transpose HZ equals 0, okay? Under that condition, I don't have a code. With this condition, I have a code in the sense that this condition is equivalent to all the matrices here commuting. If they commute, I can easily show that this is going to have a -1 eigenspace, and its dimension, if all my rows are linearly independent, will be 2 to the n minus the number of rows. So here I get something of dimension 1 in the case of this example. Okay, so this is how quantum codes are specified, just by giving two parity check matrices that satisfy this condition. And this is a little bit what makes them hard to construct in general, because let's say you want to show that there exist good classical codes. You will take a parity check matrix at random, and you will do some calculation, and this will be a good code. In the quantum case, this argument is harder to make because you need to take two parity check matrices at random under this constraint. And this is a little bit harder to analyze. It can be done. Where it becomes impossible is when you talk about LDPC codes. So LDPC codes are the ones whose parity checks have constant weight. And there's an easy probabilistic argument for showing that there exists good classical LDPC codes. And that argument is not known how to do it in the quantum case. So we have good quantum LDPC codes, but they're constructed explicitly only a few years ago, exactly on the tails of the classical, actually parallel to the classical local testable codes result. And it's not a coincidence, so why? So there's a very clear parallel between quantum LDPC codes and classical locally testable codes that I can show you on this picture. So now, if I'm trying to design a quantum code, I have to design two classical codes, the Z and the X. So Z is kind of like the classical basis, so I will change it to this picture. So I will imagine that this map now that we had before, that was our classical parity checks, is computing HZ, okay, the parity checks in the Z basis. And to have a quantum code, I need to have such a map. But I will draw on the other side here the parity checks in the Z basis. I can draw them here, okay, just for readability. Okay, so in my example, there was just one. So I can have a space here, C minus 1, F2 to the M. So now it's like X for the X parity checks. And this one is, so this is Z, this is X. And I have a map now that goes this way, like this, which is HX, the HX matrix. Okay, so this is just drawing I'm just drawing parity checks on the picture, some on the left, some on the right. However, I can observe that if I reverse the arrow, so I consider it this way, so this is just instead of computing HX, I compute HX transpose. The condition that I wrote over there, HZ, HX transpose, is exactly the condition that if I follow this arrow and then this arrow, I will get 0. Okay. So in other words, constructing a quantum code is exactly like constructing a length 2 chain complex. Before, we needed such a thing for different reasons. I had bits there, parity checks, constraints between the parity checks. In the quantum case, I have bits, and I have parity checks in one basis and parity checks in the other basis. But in the end, the object that we are trying to construct is exactly the same. It's a length 2 chain complex. This gives you the parallel. I haven't given you the definitions of distance and local testability in the quantum case. So let me just let me give you these. So in the quantum case, there's two different distances. There's a distance with respect to one of the kind of checks and the distance with respect to the other kind of checks. So I can define here dz, and this will be this, but it's the kernel. So now how did I call it? Delta 0. And it turns out that, and here I don't have time to justify this, but what you need to consider is this, and you need to remove the image of delta minus 1. So delta minus 1 is this map here. Okay. So you can think of the quantum code as being isomorphic to the quotient of the kernel of delta 0 by the image of delta minus 1. So this, and then you have another distance dx that's just the same but in the other direction. So the minimum weight of an x in the same space in the middle, such that x is in the kernel of, so usually we write these maps, this one would be called like boundary maps. So I would call it -1, and here I would have 0, okay? So the arrows in one direction or the other, they're just obtained by taking the transpose of the matrix of the map. So, and I will have exactly the same thing here. So, okay, so I get natural distance parameters. The quantum distance is the minimum of these two distances. And the local testability, I can do the same. Let me maybe not write it on the board, but I could define a z version of the local testability, and I can define an x version of the local testability. And the quantum code will be locally testable if with parameter rho, which is the minimum of these two parameters. You can show, this is a little bit of work that here I'm defining it completely algebraically, but you can connect this to some more intuitive notion of local testability, which would consider measuring parity checks at random in the quantum case and having most parity checks satisfied, and arguing that this would imply that the code needs to be close to the quantum code space. So in the quantum case, it's a little bit tricky to define like Hamming distance for vectors in C2. So I'm not doing this, but you can do it. Okay. So I've kind of arrived where I wanted to arrive, which is to define the quantum codes and think of them as higher dimensional version of the classical codes through this picture. And the task of constructing quantum locally testable codes boils down to the task of constructing chain complexes like this, where I would have local testability here, and I also need local testability here. So I don't have so much space anymore on my picture, but you can imagine that there's more dots, and I would have to add one more arrow here. So I will have a C minus 2. And my goal in constructing a good quantum locally testable is to construct a length 5 thing like this that has the right expansion and distance properties, where you have to be a little bit careful. You need distance properties in the middle, looking left and looking right, and you need expansion properties here and there. So it gets a little bit hairy, but again, these things will be constructed by triangulating surfaces, basically. Just to go back to the first part where I was trying to construct Hamiltonians, well, I did write for you a Hamiltonian here. So there was a question. This is another example of a Hamiltonian. Okay, so it's a matrix of dimension, Hermitian matrix of dimension 2 to the n by 2 to the n, and this Hamiltonian will be a local Hamiltonian if each of these p and q's is a local operator. By a local operator, I mean that it's a tensor product of identity x's and z's, such that most of the term are identities, and x's and z's only in a constant number of positions. So this will be the case if and only if my parity check matrices have constant weight rows. So this is exactly the condition of a code being an LDPC. So if I have a quantum LDPC code, I get a local Hamiltonian. Studying the eigenvectors associated to the smallest eigenvalue of this Hamiltonian is exactly studying the structure of code words. And there, I don't have time to do that, but you can show quantum code words have a lot of properties that make them very non-classical. So they don't have, they're not product states, and they don't have classical representations. Studying eigenvectors with close to the smallest eigenvalue of the Hamiltonian, this is studying states or vectors that have low energy with respect to this. So it's states or vectors that satisfy most of the parity checks, and this is where the local testability condition is coming in the picture. Of course, what's really missing here is that the smallest eigenvalue problem for a code Hamiltonian is trivial to decide. It's basically always -1 as long as I have a proper code. I just need to check this condition on the parity check matrices and so on. So it's not a hard computational problem. So there's a big step, which we don't know how to do, in going from succeeding in studying quantum codes and then managing to encode hard computational problems in them. So that's like research direction in quantum complexity that I wanted to promote, but I don't have much to say about it. So, okay, so I'll stop here.
Thank you, Thomas. Questions?
Thanks. You said that like both LTCs and also classical LTCs and also normal quantum LDPC codes are like two-level chain complexes. What are the properties required? Are they similar, or like is it just happenstance that one construction happens to have
Yeah,
both?
so it's more the second part. So it's
Okay.
not, the properties are not the same. Like if you're interested in a classical LTC, you will be studying distance here and here going this way, meaning you will look at the kernel of this map and you will also look at the kernel of this map and study certain properties of that and expansion this way. If you're, let's say on the same picture, you want to construct a quantum code, you will put the qubits here and you will be interested in studying distance this way and studying distance that way. So there's no guarantee, you can construct a cell complex that has good properties instantiated as a locally testable code and bad as instantiated as a quantum code. It just turns out that the kind of cell complexes that have been constructed tend to have good properties basically like everywhere. Actually, this is not quite the case. I mean, the fact that classically you only need to look at these maps in one direction does make the constructions easier. It makes it easier to construct them from triangulations. In the quantum case, the fact that you have to look both directions is like an additional level of difficulty.
Okay, thanks. Yeah.
Questions?
Thanks for a very nice talk. Do you have any thoughts on making a formal connection between QLTC and QPCP, or is this just really unknown?
No, I don't have thoughts on that. Yeah, I'm open to thoughts. No, I mean, even classically, this is a question that's not like understood so well. There's some intuition that says, and I, kind of like the intuition that I tried to carry, that because both of them like kind of capture the complexity of objects that are close to the ideal objects. So it seems that, and classically PCPs, I mean, at least the standard construction of PCPs is based on locally testable codes, the Reed-Muller codes, but there's many additional properties that come into play, and I don't think there's a very good sense how you'd go about. Yeah, I don't have thoughts.
Thank you.
Any other question? Last chance.
Is there, I guess before these LTCs were found, there are like older LTCs that come out of PCP type constructions, from what I understand. Like, are there ways of understanding them in terms of chain complexes that are nice? I don't know. I thought I could be wrong with this. I thought like for instance, Denora's like combinatorial proof of the PCP theorem also gives you an LTC with
Yeah, actually, so
some
Ormeyer
parameters.
worked on that, right? So, I don't know. I mean, it's a good question. My understanding is that the connection is pretty tight, so it should. But I don't know what kind of object you get. I don't know if that has been. Maybe someone. Do you know the story? No. I don't know. No.
So do people doing LTC consider other abelian coefficient, let's say Z or U1 or R?
No, so yeah, I completely skipped over that, but this whole thing that I described doesn't work by itself, so you need to, but what I'm familiar with are coefficient spaces that are themselves vector spaces over F2. So you can consider constructions where to each vertex here is assigned a coefficient which is not a bit, but is an element of F2 to some other, some small power, so it's called the system of local coefficients. So, but Z or R, this I don't know, because they're usually you don't really want to work with any infinite set because you will, in the end, you still want a binary error correcting code. So you could work with that as an intermediate object, but you would want to map it back to something that's defined over F2, which maybe you'd run into problem if you have real coefficients, for example, that seems challenging. I can imagine it maybe as inspiration or something, but eventually you'd have to get rid of that.
So you were saying in part A that these local Hamiltonians, their low energy states are hard to describe and hard to find. So if you built such a thing and you sort of cooled it and tried to encourage it to get to a low energy, is there something interesting to say about what would happen?
Well, it would probably not get there. So meaning that the cooling, I think, I mean, the physics says that if you cool the system slow enough, eventually it will stabilize into an eigenstate with the smallest eigenvalue. The problem is that that's based on like a diabatic theorem, and so if you do it too fast, the system will jump. And I think the expectation is that the cooling time would be exponentially long. So it is true that physics would just by itself find for you, would realize physically called ground state, so smallest eigenvalue eigenstate, but it would take exponential time. You know, if it didn't, then we'd have a problem with our theory. It would be exciting. So, but yeah.
Okay, let's thank Thomas for these 3 lectures. Thank you.